Hello. Now, today we are going to be looking at indices and powers, and sometimes we'll call this type of work exponents as well. But we're going to jump right into it and look at how to apply this idea of indices and powers. So, if I have 3 multiplied by 3, I know that I'm going to get 9. But there's a slightly shorter way of writing it that's going to be very useful for lots of different problems. And that's to say, if I have 3 multiplied by 3, I've multiplied 3 by itself twice. So what I can do is write down 3, and I can say it's multiplied by itself 2 times by putting a little 2 up in the corner. And this little 2 is called the indice or the power. So this says 3 is multiplied by itself twice. And I know that I'm going to get 9 as my answer. But our main focus for today is going to be on this business here, where we're going to have a number multiplied by itself a particular number of times. And this is again our indice or power. So if I look at my second situation here, I have 2 multiplied by 2 multiplied by 2 multiplied by 2. So I have 2 multiplied by itself 4 times. So I would say that that is 2 to the indice or to the power 4. So 2 is multiplied by itself 4 times. So the little number up in the top right hand corner tells me how many times I've multiplied the number by itself. Now we can combine this type of thing into different styles of questions, which is what we're going to do now. So here I have 4 multiplied by 4, and that is all multiplied by 4 multiplied by 4 multiplied by 4. So if I take each of the bigger brackets, I have 4 multiplied by 4 would be 4 to the power of 2, which we often call 4 squared. And 4 multiplied by 4 multiplied by 4 would be 4 to the power of 3, which we often call 4 cubed. Now, if I have 4 multiplied by 4, so 4 multiplied by itself twice, and 4 multiplied by itself 3 times, how many 4s do I have multiplied together in total? Well, I can count them up in this longer form. 1, 2, 3, 4, 5. I have 4 multiplied by itself 5 times. And if we look at the powers that we had on the individual numbers, on the individual 4s here, so 4 squared multiplied by 4 to the power of 3, or 4 cubed, gives me 4 to the power of 5. What did I do with the powers when I was multiplying my numbers? I ended up adding the powers. 4 to the power of 2 plus 3, I end up with 4 to the power of 5. So let's use this rule here. I have 5 to the power of 2 multiplied by 5 to the power of 4. I'm multiplying just like in the last situation. So I end up with 5 to the power of 2 plus 4. I end up with 5 to the power of 6. Does that make sense in terms of what I know about these things? I have 5 multiplied by itself twice, multiplied by 5 multiplied by itself 4 times. So I have 1, 2, 3, 4, 5, 6 5s multiplied together, and I end up with 5 to the power of 6. So that checks out, it makes sense. Now sometimes we'll have several numbers multiplied together and we'll end up with indices on multiple of them. So here I have 3 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 2. So I've put a dot underneath each 3 that's multiplied together, and I've put a line underneath each 2 to help keep track of them. This is often something we'll do when things get bigger or more complicated. So I have how many 3's multiplied together? I have 2 3's multiplied together, so that would be 3 to the power of 2 multiplied by 2 to the power of 1, 2, 3. So I have 3 2's multiplied together, so it's going to be 2 to the power of 3. And I can multiply this out completely, but this is our main concern for Earth today, that we can do going from lists like this into powers. Now let's have a look at this situation here. I have 3 to the power of 2 in brackets to the power of 3. Well, I know that to the power of 3 means I multiply something by itself 3 times. So writing this out the longer way, would be 3 to the power of 2 multiplied by 3 to the power of 2 multiplied by 3 to the power of 2. And I know what to do if I have 3 by 3 by 3 by 3 by 3 by 3. How many 3's do I have multiplied together in total? I have 2, 4, and 6. I have 3 to the power of 6. But can we see another pattern going on here? I have to the power of 2 and then a bracket to the power of 3, and I end up to the power of 6. What did I do with my powers? I multiplied them. So I ended up with 2 multiplied by 3 gave me 3 to the power of 6. So if I have a power on a bracket, I end up multiplying my powers. So let's try and apply this here. I have 2 to the power of 5 in brackets to the power of 4. That means I'm multiplying 2 to the power of 5 by itself 4 times. So I'm going to end up with 2 to the power of 5 multiplied by 4 is going to be 2 to the power of 20. It's a very big number. But does that check out? Well, I know that I'd have 5 to the power of 5 by 5 to the power of 5 by 5 to the power of 5 by 5 to the power of 5. So I'd be adding I would be adding 4 5's together, and I would end up at 20. So it does make sense that we end up with 2 to the power of 20. Now here I have 2 to the power of 3 divided by 2 to the power of 2. Let's write this out the long way. So we'd have 2 by 2 by 2 divided by 2 by 2. Now what can we see here? If we look for our common factors top and bottom that we could simplify our numbers with, I see that I have 2 divided by 2 and 2 divided by 2. So I'm left with just 2 by itself, which I would call 2 to the power of 1. So this is a normal 2. So 2 to the power of 1 means the same thing as the 2 that we're already familiar with. So what did I end up doing with my powers in this case? I ended up taking them away. So when I'm dividing the same number with different powers, I end up subtracting the powers. So the number that's underneath the line here, I'm subtracting away, and I end up with 2 to the power of 3 minus 2 is 2 to the power of 1. Now let's combine that a little bit here. So I have 5 to the power of 4 multiplied by 5 divided by 5 to the power of 3. So let's do the multiply first. I'm going to have 5 to the power of 4 multiplied by 5. Well, I know that 5, we just talked about it for 2, 5 is really just 1 5. So it's going to be 5 to the power of 1. And I know I have 4 5's multiplied together here. And I have 1 5 multiplied here. So in total, I'm going to have 5 5's multiplied together, divided by 5 to the power of 3. And I just learned that if I'm dividing like this, I'm going to subtract my powers. So I end up with 5 to the power of 5 minus 3. I end up with 5 to the power of 2. Let's apply that again here. So I have 7 to the power of 3 divided by 7 to the power of 5. And I end up taking that away, and I end up with 7 to the power of 3 minus 5. And if we're careful with this on our number lines, we'll see that we would end up down at 7 to the power of minus 2. Now that seems like a kind of a funny number. So let's do this out the long way and see what that means. So I end up with 7 multiplied by 7 multiplied by 7 all over 7 multiplied by 7 multiplied by 7 multiplied by 7 by 7 by 7. I can see that 3 of my 7's here are all going to divide out. They're all going to cancel each other out. And what will I be left with? I'd be left with 7 multiplied by 7 on the bottom line, and that's 7 squared on the bottom line, instead of it being on the top like it was before. So that's what our -2 would mean. It means that we are underneath our line. We're in a fraction type situation. Now, our next idea. This is called a square root, and it's the opposite of squared. So we started out with 3 squared here was 9. This is the opposite of something squared. This says, what number would I multiply by itself to end up with 81? And that would be 9. In terms of powers, the way that we would write this is a power of a half, because it's the opposite of 2. It's the opposite of a power of 2, or the inverse of a power of 2, to use mathematical language for it. So I would say that 81, the square root of 81 is, what number do I multiply by itself to get 81? And that's going to be 9. Now, my next point here, we've been talking about powers of 1 and powers of 3, and we even did power of -2. Here I have power of 0. Now this is an important idea for lots of different areas of maths. Any number at all to the power of 0 is always going to be 1. It doesn't matter what number it is. So I could have 199 to the power of 0, and it would just equal 1. It does not matter what the number is. If it's to the power of 0, it will always be 1. So if I take my final example here, the square root of 27 to the power of 0. We're combining several of our ideas here together. 27 to the power of 0 is going to be 1. And what's the square root of 1? What number would I multiply by itself in order to get 1? It would just be 1. So these are the different ideas that we need for right now for indices and powers.